so I'm here to tell you guys a little bit about some work that my students in my group, as well as myself, that we've been working on in the world of optimal transport, which if you don't know about, we'll give you a little bit of a crash course, and then we'll tell you about some methods there. Of course, part of my reason to trek over to the math department, which of course is extremely far away by MIT standards apparently. Like, my students are across the hallway from me, and there's this long discussion about whether that was going to be too big of a distance when they arrived last year. But anyway, part of my reason to come here is to tell you guys a little bit more broadly just what our group is about, and maybe to get you excited to come collaborate and cross all the way over to Building 32. So from that perspective, I'm going to shamelessly give you some very high-level overview of some of the different projects and ideas we're thinking about, and then we'll spend most of our time today talking about transport. I figured since I was speaking for Philippe, that should be what we focus on here. Right, so in CSAIL we have to have corny names for our research group, and the one that we settled on here was the Geometric Data Processing Group. And one of the really fun things about our research group is that we sit in between about 6 different areas, right? That we're using tools from numerical partial differential equations, optimization, and so on, but we're applying them to problems in computer graphics, machine learning, and other disciplines, right? And so because of that, we end up with like a million different affiliations in a million different places, which is essentially just a really fun excuse for us to serve as sort of consultants and collaborators in a lot of different fields. Right, so to give you guys a little bit of a flavor of some of the problems that we think about, probably the most basic one that comes up, especially because we are a member of the computer graphics group here, has to do with shape analysis, which of course is all about, well, exactly what it sounds like, analyzing and understanding typically three-dimensional shapes. And indeed we have collaborators all the way from computer animation to medical imaging for how to understand these are the sort of salient, interesting properties of a three-dimensional shape, match one to another one, and so on. One of the really interesting and fun things that sort of evolved in this piece of literature is that typically the types of tools that we're applying really are borrowed from differential geometry, and the challenge is how do we make them work on a polyhedral triangulated object, right? And this isn't just sort of old school numerical PDE where you prove some theorem about what happens as you refine your approximation. Here we're in the regime where you have some triangulated object, and that's all you got. You don't have some dense thing that you can keep sampling from until you're confident that your approximation is good. And so what we're after are sort of discrete analogs of some of the things that people prove about continuum geometry. Of course, any applied geometry group is sort of morally obligated to help folks in engineering and art and so on, solving some really challenging geometry problems. And of course, we work on things like shape deformation and meshing and these sort of things that you usually associate with a computational geometry group, I think. One of the sort of focus ones in our group that sort of evolved over the last year or two is specifically this problem of hexahedral remeshing, which I'm showing in the upper left corner here. So you're given some volume and its outer surface, and your job is to fill it with these cube-like elements, which turns out to be a topological nightmare. That roughly you're doing an algorithm where your variable is sort of an SO3 modulo the rotations of a cube, which is like a space that nobody likes to think about. But then more relevant to today's talk, what we'll really be focusing on is sort of this duality between geometric data, like 3D shapes and some of these concrete, nice objects we have in medical imaging and computer vision, as well as sort of more abstract problems involving sort of, can you put a geometric structure on a data set? What does that mean, and does it help you with different learning tasks? And then finally, recently, our group has gotten involved in a very different geometry problem, which is political redistricting. We'll save that for a different talk. So for now, what we're going to focus on for the day is a set of problems that, at least in computer science, we usually think of as correspondence. Right? So here, I believe on the left-hand side is a faculty member at Stanford in the psychology department. On the right-hand side is one of his graduate students. As we know, there's some shared structure between these two brains, but not 100%. And our job is to extract a map from the left one into the right one. Right? And this is a great example of a problem that is 50% differential geometry and 50% statistics and machine learning. Right? And the reason why is, on the one hand, it appears I'm not an anatomy person. If I'm saying something completely false, you let me know perhaps not now, but at the end of the talk. But on the one hand, it's pretty well understood that at some level of granularity, there really does exist a mapping, maybe not of points, but at least of regions on one brane onto another that preserve functionality and certain structure. But on the other hand, of course, at the most local level, perhaps we don't expect to be able to extract that, and the best we can do is ask for something smooth or low distortion. Right? And so that latter thing comes from maybe differential geometry, whereas learning structure and what things are associated with different tasks or different functions maybe comes more from statistics and learning. Right? And so our group is really trying to design these algorithms that solve different types of correspondence problems in a way that's robust. For one thing, the species of noise that we deal with is usually pretty awful, as are phone calls from my parents. But at the same time, we have to come up with extremely efficient tools and ones that sort of have nice theoretical understanding, right? So typically, we're trying to relate what we're doing to theories of differential geometry and PDE so that we have some understanding in the limit as we refine these discrete approximations, how our techniques should behave. Okay? So today, what I'm going to try and argue to y'all is that we should think about correspondence and shape matching not just as a challenging problem in itself, that we've known for a long time, but also that once you come up with extremely efficient tools for solving these, we can use it as a unit inside of larger scale and more challenging modeling problems. Right? So I'm going to tell you guys a lot about problems where the goal is not just to extract, like this point here goes to that point there, but then rather, if I have that information, can I reason over it? And for example, in the background here, I show sort of a shape interpolation task where maybe I have two pieces of geometry, and once I know how they're related, I can ask for what's the shape that's halfway in between. Right? And see, these are the kind of interesting challenges where correspondence itself is already extremely challenging, and now we're going to put a shell around the outside of it that's going to make it even harder, right? And so, of course, at the very foundation of this, we're going to need some powerful and efficient tools for matching. And then once we have that, we can kind of say, okay, well, assuming that we now have this black box, which is good at matching stuff, how can we use it and rely upon it as sort of this reliable subroutine inside of more challenging tasks? Okay? So roughly, the outline that I have today is extremely ambitious, so we'll just get as far as we get, and when we're out of time, we'll stop. So I'm going to tell you sort of the basic framework that our group has been using to kind of build up correspondence tools, which is this theory of optimal transport. Incidentally, probably if you hear Philippe give a talk on optimal transport, his perspective is quite different from my own. So we'll take sort of a geometry perspective on that world. And then I'll tell you sort of the base layer here, which is just how do we solve these transport problems really quickly. Right? For a long time, transport has been kind of known as like, gosh, it would be really great and we could apply optimal transport to all these cool statistical problems if only we could solve this linear program quickly. Right? So we're now finally at the scenario where we actually can solve transport problems relatively efficiently. And I'll tell you about some of the developments from our group on solving these sorts of things. And then we'll apply it to some more challenging things. In particular, sort of focusing on these problems that involve matching between two pieces of geometry in different contexts. And then finally, in the last 30 seconds, we'll mention like when we're trying to match between things that aren't just functions or shapes, but rather things like tensor fields, how you can extend to that case as well. As I said, probably far too ambitious, but we'll see where we get. So we'll start with a little bit of background on transport so that in case you're not familiar with this theory, or at least with the language that I'll be using to talk about it, we'll all have sort of a common ground in 30 seconds or less. So let's say that I'm in college calculus class, and my job is to understand how similar two probability distributions are. Yeah? So here I have two Gaussians over the x-axis, right, the red guy and the blue guy, and I ask you the question of how far apart are they, right? So if you take elementary, I almost said elementary school, probably middle school analysis class, the basic pipeline you might apply here would be you say, okay, well these are two functions of x, so I subtract them, I square, and I integrate. And what I get out is some notion of how similar these two distributions are, right? And of course, if you're picky, you say, okay, but Justin, these probability distributions aren't really L2 integrable. I shouldn't do that. Measures like Kale divergence are essentially a very similar flavor, right? What I do is I sort of iterate over each of these x values and just measure how similar the two distributions are. Yep. But unfortunately, if you go into a lot of computational applications, you quickly realize that these measures of divergence can get you into a lot of trouble. So one example that I think people in computer vision are quite familiar with is shown here. So back before deep learning was the state of the art for image recognition, what we used to do was you take some photograph, you're trying to compare it to some other photograph, and so you're looking for interesting features on this photo, and then you sort of compare the set of interesting features here to the set of interesting features there. That gives you some notion of similarity. So how do you detect a feature? Well, maybe what you do is for every pixel, you look at the gradients of your image nearby, and you form some little histogram. Right? So it's telling me, like, for instance, maybe the interesting part of my, the neighborhood of this pixel is largely like pointing up and to the right, or something like that. And so, for instance, things like SIFT and SURF and all these popular vision descriptors that have been totally replaced by neural networks now all kind of follow the same pattern. And unfortunately, these algorithms have kind of a bizarre property. Now, obviously, if I have a histogram and it only has one bin, it's not a super useful histogram. Yeah? In particular, all pixels look the same. So I say, OK, great. Well, computers are fast, so I'm going to start adding bins to my histogram to kind of differentiate between different directionalities, different gradient vectors. And for a while, my algorithm improves. Right? I can start detecting corners and edges and features and so on. But then what happens if I keep adding bins to my histogram? Well, if you go back to the classical computer vision sort of pipeline, these algorithms actually degrade. And why is that? Well, eventually, if you're just binning the gradients of your image, well, eventually all the pixels end up in a different bin, right? And so if you're just comparing two images by just comparing bin by bin, whether or not they have a similar gradient, you failed, right? They just look different. And so this literature has this kind of bizarre science where you have to choose some number of bins that's not too big and not too small to get the right granularity you need, but if it's too big, you get into trouble. So somehow there's something a little strange there. Right? And this is something that shows up a lot in statistical language. So here, for instance, I've shown you 3 different histograms. Right? So here, this guy is centered just to the left of 0. This one's just to the right of 0. This is all the way at x equals 5. Right, these different bins. And I would argue that there are a lot of contexts where distance along this horizontal axis actually is meaningful, right? But any measure of divergence that just sums up per bin isn't going to see that. OK, so what's the big idea in optimal transport? It's extremely simple. Everything I've told you about so far compares vertically. Optimal transport compares horizontally. Right? And that's the basic setup for sort of some alternative way of understanding probability distributions, specifically when they're supported over a piece of geometry like the x-axis here. Okay? And the basic intuition is one of these ideas that sort of has been invented and reinvented in like every single discipline possible. Certainly statistics, measure theory, computer science, I think ecology we found. And of course, in each case, this person names it after themselves and says, we've got this brilliant new idea that's never been seen before. But the basic idea here, I think the most expressive name for this comes from computer science, where they call it the Earth mover's distance. Right? So here, the basic idea is that maybe I have 2 probability distributions that I think of like piles of sand. And now I'd like to measure how similar they are. So what do I do? Well, sort of there's some amount of work that I can take to scoop up one pile of sand and drop it onto the other, right? To transform one into the other. There are a lot of different ways I could do it, right? I could scoop one up, take a lap around the room, give Matt a high five, come back and drop it on the pile over here. Or I could do something more efficient, right? But somehow intrinsically, as a property of the 2 piles of sand, there's some minimal amount of work that it takes for me to transform one into the other, right? Because they're just not the same. I got to at least pick up 1 grain of stuff. Yeah? And of course, since I've moved from California to Boston, I'm intimately familiar with this. In fact, the first time I gave this talk, this is what it looks like outside of my house. Right? And try as I might, if I just look at the snow, it doesn't move itself. Yeah? So under the observation that even the laziest shoveler has to do some amount of work, optimal transport is exactly that, the minimal amount of work it takes to transform one distribution into another, treating them like piles of sand. Right? So if we want to formalize that a little bit, let's say that pi of x comma y here, I'm going to be extremely sloppy here, by the way. This is a measure. I can't even write it as a function, but we're just not going to even worry about that here. We're going to think of pi of x comma y as how much sand I move from x to y, or snow, I guess, here. Yeah? And I have 3 constraints. One is I can't move a negative amount of snow. The next one is that, if I marginalize over y, I get the input distribution. So in other words, every particle of snow has some target. And if I marginalize over x, I get the output distribution. So every particle of snow has to go somewhere. Yeah? These are sort of all of the possible ways that I could dump one pile of snow onto another. And then essentially what optimal transport says is that over this set, over all the possible couplings, that's what this notation is here, I want to minimize the integral of some measure. So for instance, distance here would be the total amount of work, which is kind of what I'm talking about here. Yeah? This is called the Kantorovich Problem. And there are all kinds of beautiful theory and applications of this particular construction. In particular, when c of xy is some power of the distance from x to y over a piece of geometry. Right? So in this case, this is known as the Wasserstein distance. Embarrassingly, only fairly recently did I realize that Wasserstein is still with us. But that aside, you can see that essentially the p-Wasserstein distance is exactly the cost of moving snow, where the amount of money that you pay to move from x to y is proportional to the pth power of distance. Yeah? It turns out the p equals 2 case is particularly nice. It kind of looks like kinetic energy as opposed to work, but that's something that doesn't matter quite so much at the moment. Okay, so in case you weren't familiar with optimal transport, now you are. So with that, let's tell you a little bit about sort of what we focus on in this particular area. Incidentally, this is like the tip of a giant theoretical iceberg in case you're not familiar with this particular branch of analysis. So here's the thing. Let's say that we're in the computer graphics group, and in an effort to make our work look as unserious as possible, we have this 3D teddy bear on the bottom left here, right? And it turns out this is pretty typical for the type of data that we have in the graphics world, where it's somehow a very simple embedded 3D object that's triangulated. But even for this extremely simple shape, he's composed of, I think, on the order of 20,000 polygons, right? And let's take a look at transport through the lens of this teddy bear here. So, right, so if I kind of take what I gave you before and translate from measures to a linear program, right, then my unknown is now Tij, this amount of sand I move from vertex I to vertex j. Right, so my two constraints are that I start with distribution P, I end up at distribution Q. I have to move a positive amount of mass. And over all the ways to do that, I pay the total amount of mass times distance. So what goes wrong? So if I'm a computer science theorist, I'm done, right? Like essentially this is a linear program, it's solvable in polynomial time, life is good. But unfortunately, of course, the number of unknowns in this problem is staggering, right? It's quadratic in the size of the teddy bear here, and he has a lot of vertices. And you might say, okay, but Justin, if you're really sneaky, you say, well, the convex dual of this problem actually have a linear number of unknowns, so it's not clear that that's the main issue. You're right. But even writing this problem down often will overflow my laptop, because the cost function here, d of xi xj, well, what is it? It's the shortest path along the surface of the teddy bear between every pair of points. Right? So before I can even pose this problem, I have to compute pairwise shortest path distance along a complicated object. Incidentally, it turns out that the shortest path along triangle edges is a really bad approximation of shortest path along the surface. That's the topic. If you like that kind of stuff, you should take my class next year. But the basic takeaway here is that I can't even write this problem down, let alone solve it. And if I'm in the computer graphics regime, where there's this magic number of 29.97 frames per second that I'd like to hit, just to throw out a number, if you don't know, that's the frame rate of your eye, we're certainly not going to get it by posing a problem this way. No? OK, so essentially, at this point, we have many years of research tackling this problem from just about every possible angle, and then applying it in some interesting contexts. So the first one, which I think aligns the closest with sort of the setup that I've given you so far, where you're paying mass times distance for the amount of stuff that you move, was actually something that we presented in Subgraph at this point a few years ago. Since I'm in the math department, I'll take my 30 seconds to remind all of you guys that in fact, computer graphics has some really cool, non-trivial, interesting math. So if you're not used to looking in these articles beyond these nice 3D figures, I encourage you to dig a little deeper. But anyway, hopefully this is one nice example. So here, the basic idea here is to leverage a nice connection between PDE and optimal transport, which has been known for a while, and actually was proposed originally in the computational world, but then kind of neglected in the computer science part of the computational world. So in particular, actually maybe I will draw a little bit on the board. So let's say that I have a graph. Nope. oh, it's this terrible chalk. And I want to move 1 unit of mass from this vertex to this vertex, okay? And so how much money do I pay to do that? Well, I pay once along, assuming it's linear, I pay once along this edge, once along this edge, and once along that edge, yeah? And of course, I think most computer scientists would agree that that linear program that I wrote down is sort of like the worst possible way to solve this problem in this case, because I could take my original problem and split it up into one variable per edge, right? And what do I get? I get that what I'm really trying to do is, I hate this chalk, wow.
There's some chalk in the box in there.
Oh, is there? Great. I'm trying to minimize the total flow over all the edges, subject to the constraint that the flux in or out of a vertex is equal to the difference between your two distributions. This is an easy thing to check. So the kind of interesting thing is that even on a continuum domain like a surface, essentially the same formula ends up carrying through. And in particular, you can show that this one Wasserstein distance is equivalent to something known as a Beckmann problem. So this is essentially a problem where you're prescribing the divergence of a vector field. And this vector field in 1 unit of time, it vects from row 0 to row 1. Notice I use the word advex. So here I'm thinking of the mass of my probability distribution kind of like a density of a gas. And I'm saying I have 1 unit of time to transform that gas from one pose into another. Right? And over all of the possible ways to do that, I want to minimize the total amount of work that I do. And it turns out sort of the correct notion of work here is the integral of the 2 norm of your vector field not squared. So sort of aesthetically, this is really exactly the same as this graph theory problem here, right? Here, instead of flux in or out of vertices, I have a divergence-constrained vector field. And my objective function, which was an L1 norm there, ends up being sort of this funny mixed norm of the vector field here. So why does this matter? I mean, in a sense, it looks like I took a complicated problem and I made it worse, right? I introduced PDE language into something that was already kind of messy, right? But what did I gain? Well, there used to be two indices in my unknown transport matrix, right? T, I, J. But here, I only have one unknown per point, this J of x, right? So from a computational perspective, we're already doing pretty well. I don't need a quadratic number of things to solve this problem. And in fact, to make matters even better, there's no distance matrix here. This is completely local, right? And so at the end of the day, it turns out this problem can be solved extremely efficiently using one more magic trick. This is another great, the reason I'm harping on this paper a little bit, because it's a great example of sort of having 1 foot in continuous world and 1 foot in discrete. So the next trick that we'll use is something called the Hodge decomposition, which you might remember from calculus class, which says you can take any vector field and decompose it as the sum really of 3 pieces, but here we're going to talk about 2, of the gradient of a function plus on a surface, the gradient of a function rotated 90 degrees in the tangent plane. Right, so this is a curl-free vector field. You can see that like it doesn't circulate, it just compresses. And this is a divergence-free vector field, it circulates. If you're doing this problem on a donut, you also have to deal with harmonic component, which like goes around the outside of the donut, but we're not going to worry about that for now. So I'll refer you to our paper for how to deal with that. So here's the thing. Any vector field can be decomposed this way. So in particular, let's say that instead of my unknown being J, I'm going to replace it with F and G. Okay, so remember that I have a constraint on the divergence of J. What do you think the divergence of a divergence-free vector field is 0. So what I'm left with is the Laplacian operator applied to just this one piece F. And here's the thing. This is basically an invertible matrix. This is a Poisson equation, right? So I can solve extremely cheaply for this function F, and what I'm left with is an unconstrained problem for the remaining piece G, which just looks like an L1 norm, like the kind of thing that we know how to do really well in compressive sensing well. Yeah?
So in the purely discrete
graph, you get in trouble here. Yeah. So in the discrete graph theory land,
so
this is rank nullity theorem.
Into circulations and flows.
Exactly.
Now,
it's precisely the same.
Interpret this through duality instead with the.
It's a good
because you can
question.
create heights along the vertices and express the flow that way.
Yeah, so your version of heights is what we would call potential in differential geometry. But yeah, I guess that's right. But there's one really irritating difference. So remember in this picture here, there are these 3 terms, and I kind of neglected the donut term. Yeah, so In the theory of like in the cohomology of surfaces, we know that the dimensionality of this looks like the Euler characteristic, like the number of holes. On a graph, the dimensionality of that becomes huge, and so it ends up that this trick doesn't help you quite as much. This is actually an open question that I'd love to bother you about, because something that would be really great to have would be like a basis for harmonic vector fields that somehow takes care of big circulations before small ones, and as far as I know, that doesn't exist. But we'll come back to that.
Perhaps in like geometrically embedded graphs or something.
Absolutely, yeah, like including these things, which are just triangulated surfaces. Yeah, right. So what can we use this for? Well, one of the kind of fun applications that we threw it at, which is a little bit circuitous, is actually computing the shortest path between 2 points on a triangulated surface is actually kind of a tricky problem. And so one extremely bizarre way that you might go about this is actually to put a delta function at 2 points on your surface, compute the transport distance between those delta functions, and what you get as a side effect is the distance between those 2 points. And the really surprising thing is that this is actually competitive with state-of-the-art sort of geodesic distance approximation on a surface, which caught us by surprise. We thought this was going to be like a fun side project, and it actually is quite effective and kind of an easy way to carry out a computation like this. Okay, so...
Actually, I have one more question. So,
okay.
Well, let's say hypothetically, so if you take a triangulated surface,
Uh-huh.
I can also, if I wanted, I could define a sequence of triangulations if I had it.
Mm-hmm.
And do any of these algorithms amortize well?
Amortize well.
So, for example, if I had a solution for some transport problem on a coarse thing, partially.
That's a great question. So there's a gentleman, Bernhard Schmitzer, in Germany, who studied this a little bit. You have to be so you have that transport matrix, and you might expect to be able to kind of rule out different pieces of it. You have to be extremely careful how you do that. I don't know if there's consensus from a theoretical perspective whether there's a way to do that systematically without accidentally, like what you wouldn't want would be like in your coarse version of your problem, you say, okay, I don't need this piece of the transport matrix. Then it turns out when you refine, you do. I don't know if theoretical results like guarantee that you do the right thing, except in very restrictive case. It's a good question. Yeah, I don't know. Right. So, of course, I told you we spent many years studying transport problem, and I just gave you a solution. So why aren't we done? Yeah. Well, there's a lot of drawbacks, especially of this one Wasserstein distance. So here I'll show you kind of a funny plot. So the way to read this is that the vertical axis is your distribution, like it's one-dimensional, and the color is the height, right? So this is like a Gaussian. And let's say that I ask for the distribution, which is sort of the midpoint of two other ones. So I sum up the transport distance from row to row 0 plus the transport distance from row to row 1. And I want to find the row that minimizes that. So it turns out if I do that with respect to the distance that I showed you before, the interpolation that I get is this thing up top, which is extremely uninteresting. Right? This is like interpolating two distributions by taking t times one and 1 minus t times the other. Right? So it does that. Right? Whereas sort of our intuition from transport tells us that we'd like to do that. Right? We want to move mass horizontally. Yeah? And it turns out this is a property associated with the 2 Wasserstein distance. That hiding inside of this guy might be one of many non-unique solutions that look like the bottom one. But here this is the unique one, and this is called displacement interpolation. Yeah? So, right. So naturally, as computer graphics people, we look at an image like that, and we get very excited because it might allow us to do things like not just interpolate between Gaussians and mixtures of Gaussians, but rather between cows and ducks and torus objects. And of course, that's what we set out to do next. So here, these are kind of level set functions of a function supported in a cubic grid, and that's what we're interpolating between. So the trick here, and kind of surprisingly, like spiritually, you need a completely different computational trick, which caught us by surprise. The idea here is to not solve the original transport problem, but actually to regularize it a little bit. And it turns out this was a very popular idea in numerical transport just more broadly. It was introduced introduced to the computational world in 2013 in this newspaper by Marco. But the basic idea is, I'm sorry I'm switching between discrete and continuous notation a little bit, but hopefully at this point you can kind of eyeball like distance times mass. It shows up a lot of different forms. We're going to augment the original optimization problem with a second term, which measures the entropy of your matrix. Right? Notice there's a minus there. So as I increase gamma, essentially my matching, which used to be like this sharp sort of graph matching from one distribution to another, becomes more and more fuzzy. Yeah? But what I get in exchange for that fuzziness is an extremely efficient algorithm for computing transport. Right? And the reason is just high school algebra. That it turns out, if I regularize the problem using entropy, I can write it in a very different way, which is a KL divergence. Right? This is some measure from information theory of distance, roughly, between your transport matrix and this kernel that I've defined for you here, which is e to the minus distance squared. Yeah? So why does that matter? Well, KL divergence is some notion of distance. It's a different notion of distance from Wasserstein. It is a notion of distance. And this gives you an interesting interpretation for this transport problem, right? What it's saying is, I would like to find the pi that's closest to this matrix on the right-hand side. But remember, there are constraints on pi, that it's rows and columns sum to your input and output distributions, right? And so roughly, the algorithm, actually we'll come back to this in a moment. For computing this, is extremely simple. It's just alternating projection. You start with your matrix, e to the minus distance squared. You'll see I'm using h for a reason in a moment. And then I'm going to project onto just the matrices whose row sums are prescribed, and then just the matrices whose column sums are prescribed, and so on. And it turns out that one thing you can show quite easily is if I want to take a matrix and project it onto the ones whose row sums are known, what do? Well, I take the sums of the rows, and then I rescale the rows so that they sum to the value I wanted. So this algorithm fits in 3 lines of code, right? So I start with h, I rescale the rows, I rescale the columns, I rescale the rows, I rescale the columns, and that's all. Yeah? So this is called the Sinkhorn algorithm. It's extremely simple. But it still requires you to know this matrix H. And actually for us, that's not so good. Yeah? So the one additional thing that you can observe, what is H? It's just a Gaussian in distance. Yeah? So if I multiply by this matrix H, that's like taking a signal and blurring it out. That's all it's doing, right? And so the basic observation in entropy regularized transport on an image is that you never actually need your cost. All you have to do is to be able to blur stuff out really fast, right? Because I only ever have to multiply by h. I never have to keep it around. So at the end of the day, you get a linear time iteration for this problem by being really sneaky and never writing down your cost. Just multiply by a bunch of times, which essentially, for example, on an image, how do we blur stuff out? It's using the fast Fourier transform, right? Which is what? N log n time. Now, H here stands for heat kernel, right? And one question might be, can I also carry out a similar approximation on a curved surface? And in fact, to do that, I'm noticing I accidentally removed that slide. You can. And the trick is, let's say I want to solve the heat equation, right? That's du dt equals Laplacian of u, plus or minus that. Geometry and computational people can't decide on the sign of the Laplacian matrix, but that's for another day. One thing you can prove is that for short time, if you take the log of that kernel, like the thing that's blurring out, heat equation blur stuff out, the log of that looks like geodesic distance squared. We already kind of knew that, right? Like if the Gaussian is the heat kernel on the plane, and of course you take the log of the Gaussian, you get x minus y squared, right? So this is essentially just an extension of that fact, right? So what do we do? Well, it's a little bit of a language trick, but then you go back and you prove that it's okay. You say, okay, well I'm going to define a new regularized transport distance, where like the matrix I really want here is this kernel defined there, right? Where maybe this is geodesic distance along a surface. That's hard to compute. But I know that this thing and the heat kernel look kind of similar, so let's just throw the heat kernel in here and then use that in our algorithm instead. One thing you can prove is that if you take the limit as t goes to 0, right? So in other words, the amount of diffusion that you do gets really small, you still recover the transport distance you want. That's actually kind of an annoying proof to do because it turns out the species of convergence of the heat kernel is not the same as the one that you need for transport, but that's a detail for another day.
Sorry, in the practical example, what is the manifold you're talking about here?
Right, so in this case, actually, these are the manifold is super boring. It's just a cubic grid that's sitting around it, and I'm showing you the 0 level set, or I guess the 1/2 level set. Unfortunately, because I was so excited to share like a million different things that I didn't actually include an image of what it looks like on a surface. But trust me that it works. And roughly the output looks very similar to these kinds of techniques. But with the added benefit that like if I have different signals on a curved surface, I can now interpolate between them in a way that actually moves along the surface. Okay, sorry about that. Right.
In your formulas, if you have to tune 2 parameter, well, so the one with the heat kernel, not this slide.
Oh.
Yeah. So in that last slide, you have a t. That just the square root of gamma.
Yeah. Used to be, I think there's a 2 in there, but yeah, there's some formula that goes from one to the other.
So you really only have one parameter that you're choosing when you decide
Yes.
how to regularize.
Absolutely. Which is a great question, and in fact motivates why this algorithm isn't sufficient for a lot of problems. Because in particular, what does the heat equation look like as t goes to 0? Well, it looks like nothing, right? It looks like the identity matrix, right? And so we're somehow in this regime where we'd like t to be positive because that's where we know how to do computation. At the same time, we'd like to be as close to 0 because that's where we get the real solution to the transport problem, right? And so, unfortunately, as you say, there's this tricky parameter that you have to choose that's sort of your trade-off between accuracy and speed. And that's a difficult one to choose. And in fact, if you really crank up the accuracy, you take that t to be very small, this algorithm ends up dividing by 0, which isn't so great. So in reality, what you get is very fuzzy stuff, like on the left-hand side. Now, of course, if I'm presenting this to a computer graphics audience, what I'd say is like, look, we're really good at taking fuzzy stuff and making them sharp. Like, that's the thing graphics people know how to do. So we're kind of OK with this output. But of course, that's a little bit of a cop-out, right? What we prefer is to really get an interpolation that doesn't look like this kind of painful eyeglass-free interpretation of interpolation. Yeah? So in particular, this stuff is fuzzy, and that's not so great. So naturally, the next problem we set out to solve was can we solve this without all this fuzziness? And we have some initial results on this in a very different context. And one of the questions, one thing I've been bugging Philippe about is kind of putting all of these things together with the geometry papers that we had before. Right? So this SISC is like the SIAM Scientific Computing Journal. So it's a very different context. So here, we're looking at transport along a graph, right? And so if you recall before, that's exactly the same as that PDE problem we had before. Notice, by the way, I can get rid of the absolute value by just having an edge doubled forward and backward. But now, one question you could ask would be, OK, let's say I solve network flow on a graph. For instance, the one on the top here is a good example. In fact, I talked to some people at some shipping place or another, and they actually run into this problem, which caught me by surprise. If I every day I wake up, I get a slightly different supply and demand that I'm routing stuff between. What do you think happens? Well, I give my truckers a completely different roadmap of where they have to go to deliver stuff, right? And there's a question, which is how much of that is because the transport problem really has changed. The distribution of supply and demand is a little different, and now I have to ship a completely different way. And how much of it is just because it turns out that the solution of this problem is extremely non-unique, right? Like, so for instance, here, if I have 1 unit of mass at these 2 vertices, I want to move it just to the upper right. Well, there's 2 different ways I could do it, right? I could go on kind of the upper envelope here, or along the lower one, and they induce the same cost. Right? And so one question you might ask is just, OK, how do we go about breaking the tie? And the sort of standard way in convex analysis would be maybe add a little bit of a least squares term. Yeah? So this is a completely reasonable trick. But of course, the second that you do that, what happens? Well, your nice network flow algorithms you had before are no longer applicable, right? You need something new. OK, so once again, this sort of routing supply to demand problem takes exactly the same form. But now this cost matrix D is like shortest path along a graph. Yeah? And as we saw before, we can write exactly the same Beckmann formulation where essentially this J here is taking the place of the vector field that we had before. You'll notice, by the way, like my background is in PDE and differential geometry, but I'm in a computer science department, and I think I'm motivating this completely backward from how my colleagues would think about this stuff. We actually started with the PDE problem, and now we're back on graphs. Right, but in any case, the basic issue in a lot of applications is that the solution is just not unique, right? And there are a lot of different ways with completely equal cost to flow from one configuration to another. Yeah. And so the first question we wanted to ask, what is the simplest way to break that tie? It's also the least useful one. We'll come back to that in a moment. Would be to add a least squares term to this problem, which says I mostly pay mass times distance, but I also pay a little bit mass squared times distance. This is not mass times distance squared, by the way. OK. And what you get out of this problem is that now it is strongly convex, meaning that it has a unique solution. The reason why I mentioned that it's not necessarily the solution you want is that what do you get? You get the superposition of all of the ways of moving from A to B, right? So if you really are running a trucking company, it's not clear whether this is the right thing to do or not, but that's okay. So one thing that you can prove, our proof is like a little technical and nasty. My hope is that someday somebody can tell us why it's really like a two-liner, is that if you take this parameter alpha and you just increase it and you look at the sparsity of your flow as a function of alpha, what you expect is that the sparsity decreases, or the number of edges on which there is flow increases, which kind of makes sense because least squares wants to spread stuff out. And indeed, you really can prove that you can control it with this parameter here. But this is a really important property for us because in the entropy regularized version of the problem, what happens? You take your regularizer to be anything other than 0, and there's automatically mass everywhere, is the property. So here we show that doesn't happen. You really can control it. OK. So to solve this optimization problem, we need yet another technical tool that looks completely different from the last two. This is somehow something we haven't sort of philosophically got to wrap our hands around. But here, essentially, we take the convex dual of this problem. Right? We know for every convex problem, there exists another convex problem you can solve. So if you have a minimization problem, there's a maximum one that leaves you a lower bound. And in this particular case, gives you a tight lower bound. And essentially, what you end up with is finding one potential per vertex, and where you have an optimization problem. Here, F is the difference between the supply and demand. Makes sense, because if F is 0, then you kind of don't want anything to happen. And essentially what you get is a linear term minus this quadratic term, where D is an operator that takes one number per vertex, and then for every edge just subtracts. Right? So you can think of D like a gradient. Right? So like for instance, here, if I had a 1 and a 2, and I orient, doesn't matter how I orient the edge, right? Then I'll have 2 minus 1 is 1, 1 minus 2 is minus 1, and so on. So that's what this operator is doing. OK? And then this plus sign indicates that I take only the positive elements and the 2 norm of this thing. So if that plus sign just weren't there, life would be pretty good, right? Because then it's a least squares problem. We know how to solve it. Yeah? But sadly, it ain't. So let's think a little bit more about what's going on in this problem, right? So remember that I'm kind of thinking about D as some kind of gradient operator. Yeah? And really a different way of looking at this is, like if I just take the positive part, this thing is really equal to, I could take some other matrix, we'll call it S for sine, times dp minus c, where this is just diagonals of 0 and 1. It's just turning off non-negative things. Right? So it's a function of p. Yeah? OK. And then I take the 2 norm of this object squared. OK? So if I want to do numerical optimization on this problem, typically what I need is the Hessian matrix. And in this case, what does it look like? Well, S squared is obviously equal to S. Yeah? So we get D transpose times S times D. The question is, what is this matrix? Yeah? So let's pretend S wasn't there. So then it's just sort of like, this is gradient, so gradient transpose, kind of like divergence. Yeah? What's div of grad? It's a Laplacian. And in fact, this matrix is the graph Laplacian. And what is this S thing doing? It's just turning off edges. Yeah? So all this is it's the Laplacian of the graph restricted to the edges where there's flow that's non-zero. Yeah? And so in fact, this problem isn't so hard to deal with, that if I want to run Newton's method, which needs a Hessian matrix, it's actually quite easy to compute as a sort of a Laplacian on a restricted subgraph of the full object that I had. Yeah? And so the final algorithm is extremely simple. You just multiply the inverse of this thing times the gradient. Right? That's Newton's method. You just keep multiplying with the inverse of the Hessian. OK. Now, we're not completely out of the water yet, because inverting that matrix is kind of pricey. And so to deal with that, we have sparse linear algebra helps. Like you know that there's really only non-zeros where there's edges in your graph. But that's still not great, because the sparsity pattern changes every time you add or remove flow on your network flow problem. Yeah? So to go around this issue, we make one more observation, which is let's say that I just perturb this vector p a little bit. Well, what ends up happening is, I slowly perturb p for a long time. The edges where that number is positive remains the same. And finally, one sign flips. And what do I get? Well, I get one more positive number, one more negative number. And that's when the sparsity changes, but only by one edge. Right? And so you might be familiar, there's actually a formula that says if I take a positive definite matrix and I add or remove a rank 1 component to it, I can just get a formula for the inverse of this guy in terms of the inverse of this guy. Right? So in fact, this algorithm is extremely simple. I invert my Laplacian once in iteration 0, and then as I do my optimization, all I have to do is make small rank 1 updates to this matrix and continue. Right? And so that's our final algorithm here. You begin by computing the Laplacian of whatever your initial guess was. And that has some sparse Cholesky factorization. The details don't matter here. And every iteration, you choose your search direction, like for Newton's method. And you do line search until a sign flips. And then you update your Hessian and you keep going. There's one tiny detail here. This is a piecewise quadratic objective function. And occasionally it's just flat, like the quadratic part just vanishes, in which case Newton's method fails. There's something that smells like a hack, but actually is theoretically justified, where if you do every other iteration as gradient descent, then you can guarantee that you get out of that hole if it happens. Yeah. OK.
I have a couple of questions. The first one is gradient descent going to be too slow for this?
Yes.
The scale of the problems you had in mind?
Yeah, even for small problems, it turns out gradient descent does not grate on these kinds of min-cost flow problems. Yeah. Of course, if you add like a ton of quadratic regularizer, then it'll probably do OK. Actually, even in that case, Laplacians are not the best conditioned matrices in the world. And so you can still run into some trouble. You might as well do conjugate gradient in that case. Right? Right. OK, but hopefully I've at least convinced y'all that we have a lot of different tools for solving basically every instance of transport we see in sort of geometric practice. And the basic insight that we've had in each of these projects is that it's not enough to just consider that linear program. You also need to know a little bit about the structure of your cost, right? That whether it's some triangulated surface where you can write in PDE language, or a graph where you can think about it in terms of Laplacian and shortest paths and so on. Yep. So as usual, I'm way over time, but I'll briefly sketch for you guys some ideas of how we can now build upon this. You can see that the optimal transport is sort of a basic matching tool, and now we can build more advanced things on top of it. Yeah. So let's start with the problem of the Wasserstein Barycenter. So here, I'm in the graphics groups. This is kind of a shameful animation here, but this is the best I could do in MATLAB. So let's say that I have 3 different probability distributions over the real line, like the red, I'm not colorblind, red, green, and blue here, and I'd like to interpolate between them. Right? So of course, the simplest thing to do is to kind of take barycentric coordinates that correspond to your weights for these 3 guys, and then just average them with those 3 weights. And what you get is this interpolation on the right-hand side. So you can see that, again, the peaks just kind of grow and shrink. Right? But of course, if you're in the geometric regime, then what you might expect for your interpolation is that information actually moves horizontally, because the x-axis is what's giving geometry to this problem. Right? And so one way to carry out that interpolation is to say, well, I have a bunch of probability distributions mu I. Right? Those correspond to these 3 guys on the vertices of the triangle here. Now, what I'd like is the distribution mu, which sort of minimizes the sum of squared distances to the 3 guys. Right? Here, I guess there's really weights in front of the W's. Yeah? And that's what I'm showing you here. In fact, there are even more interesting problems that essentially involve extending from just maps from that extend. Let me try that again. There are even more complicated versions of this problem that look like Dirichlet problems in differential geometry. So here I have, for example, a graph, and every vertex of my graph is labeled with a distribution over another domain, right? And my job is to impute the missing distributions, right? So maybe I have my social network, and I only hang out with wealthy people, and I have some distribution over wealth that I know at a couple isolated vertices, and what I'm trying to infer is the distribution elsewhere. Right? So under the assumption that nearby people have kind of nearby distributions in the Wasserstein sense, then maybe what I do to impute is to sum over all the edges the transport distance and then try to find the value at every vertex. This is the extension of sort of a semi-supervised learning problem that we all know and love for scalar values here. And in fact, one thing we studied is sort of what is the differential geometry version of this. So like if I map from a sphere into another sphere, then I can kind of, if I take a tangent of my map, right? So I have a map from one surface into another. Now I look at a point, and I take a vector at that point. Then my map gives me sort of an image vector on the target surface. So in this measure value case, I no longer get a vector, but a vector field, and then we've worked out that theory. But anyway, ignoring the theory part for now, because it's quite weak. We have a visitor in our group that's going to help us fix that. We're back to this challenge that entropic regularization gives you some notion of average, right? These are all barycenters here, but they're fuzzy. Yeah? And so I give you one of these issues to overcome, and then another one to overcome in the machine learning context is that typically we don't have access to probability distributions as functions. Right? We have access to them as samplers. Hopefully you see the difference. So in optimal transport, the way that I've written this down, I have this unknown measure whose rows and columns sum to these two distributions. Right? So implicitly, I'm assuming that I have access to those two distributions. But for example, if I'm doing Bayesian machine learning, where all I can do is just sample from some posterior, I don't actually know the function itself, I just can draw samples from it. Right? The question is, can we compute sort of sharp, nice barycenters in this case where all I can do is sample? I can't get the distribution function itself. And this has been sort of something that we've been focusing on with my student Sebastian, and also with Matt here, including two papers, one at NIPS and one that we just submitted recently. And hopefully, with apologies to Matt, we'll actually sketch out very briefly the latter here. So the basic setup here is I have a collection of probability distributions that I'm viewing as black boxes. And all these black boxes can do is just spit out samples from these distributions, one at a time. Yeah? And the question is, can I come up with a procedure that assembles the average of these distributions with respect to the transport distance? Okay, and that's somehow some geometric summary of your input distribution. So for instance, like imagine that I have a car and it has these different sensors. They're collecting data. The sensors are slightly misaligned, but they're extremely confident sensors. Right? So what would happen normally if I average the signal? I get an extremely unconfident signal. But it might be that really the right thing to do is to just kind of align their distributions and keep a lower variance. Again, not in all applications, but in some. So in this case, we use yet another completely different version of optimal transport that makes more sense for empirical distributions. I'm sorry, I'm realizing now that this is talking all over the place. Anyway, so here, the idea is that I have one distribution which is a collection of points, and I'd like to map it to something that's like a continuum, right? And the reason this is my basic setup, I'm going to try and approximate this barycenter with an empirical measure, right, with a bunch of points. And I know nothing about my input distributions, right?
So you don't have any Lipschitz condition on them, or like some sort of kernel density estimate?
I think to prove something about them, you might need that they're absolutely continuous with respect to the measure underneath. But no, we don't make that assumption to set up. So because we don't have access to them, all we can do is sample. We know nothing about them. Yeah. So it turns out it's not so hard to show that actually, if you have transport from a discrete distribution, like a distribution supported on a finite set of points, to any distribution, you can compute that using a finite number of variables. And essentially, the way that you do this, you take the dual of this problem, and you show that it kind of looks like a Voronoi problem. That what you're doing is you're trying to divide the plane up into these little cells that are assigned to each of the points of mass. Right? This is not quite Voronoi because Voronoi cells don't have the same size. So to correct for that, you compute something called a power diagram, which is kind of like Voronoi where your distance is shifted a little bit. Yeah? Or a lot, actually, there's no. Right. So to compute an empirical barycenter approximation, what do you need? So you have your barycenter is some collection of points xi. That's on the left-hand side. And what is your optimization problem? Well, if you're in the dual of transport, which is how you get this nice finite number of variables, then you have for every, if you think about it, you're trying to compute transport between this unknown collection of x's and each of your fixed distributions that you're sampling from, right? So to do that, each of these x's is associated with a dual variable for each of those transport problems, right? One per input distribution, right? So you end up with this sort of matrix of 5 values here. And your job is to solve a minimax problem, right? You're trying to minimize over all of the configurations of these point x, the thing that solves transport, and the dual of transport is a maximization problem, yeah? And so there's a relatively simple algorithm for solving this, where you kind of alternate between updating the x's and updating the phi's here. Right? So the phi's, this is a concave problem, so you can just use gradient descent. And the x's out here, it turns out, have a very nice sort of fixed point iteration that just looks like k-means. Right? You kind of, this already looks like an averaging problem. Right? You're trying to kind of summarize a cell in your Voronoi diagram. So essentially, you alternate between moving points to the centers of their power cells and then doing an update on these dual variables. And what you can show is that this thing converges at least in objective value. doesn't converge necessarily to the global maximum. This is actually non-convex thanks to this axis, which is a little bit tricky. But if we skip to results, we can see some really nice things happening. So here I have a bunch of different probability distributions that are all supported on different circles and ellipses that are just kind of randomly drawn. And I compute the Barycenter distribution, and what we get as our approximation is actually a circle. There's a little bit of mythology here. We don't actually have a great explanation for why, although I guess there's some symmetry argument you can make. And of course, state of the art before this, because they add an entropic regularizer, you get this very fuzzy kind of ring of information here. Or similarly here, if you have a collection of distributions that are on line segments, you end up with kind of a segment-like Barycenter. This, by the way, I think motivates some interesting research just into transport, like why does this happen? Whereas, well, our previous method unfortunately fails here with respect to my colleague back there, and the entropic thing again gives you kind of a fuzzy result. One interesting special case that computer graphics people like essentially says, what if I want to approximate one distribution with something empirical? And what you recover is something called blue noise. So this would be like an empirical distribution that geometrically kind of resembles a distribution underneath it. And this is, so like if you have a black and white printer and you're trying to print a grayscale image, then you might want to compute a pattern like this. It's also extremely important in paper submissions to have a cute puppy that makes the reviewers feel bad, rejecting your work. So as usual, I think I'm about out of time. I'll very quickly sketch just what we're thinking about in matching problems here. Essentially, all of the matching problems I've shown you so far, the geometry is provided by the domain that they sit on, right? In optimal transport, like the geometry isn't the geometry of the piles of snow, it's the geometry of the pavement that I'm walking along. That's where my cost comes from. If you think about that problem where I'm matching two brains to each other, right? Like if I'm matching my brain to Mazzy's brain, like if he walks to the other side of the room, it's the same mapping, right? So somehow that's not exactly the right model. And so in that case, what we need is something that's sort of rigid invariant, right? That doesn't care about translation, rotation, or even maybe some kind of elastic motion, right? So in that case, this is the regime of quadratic assignment instead of linear assignment, where you're sort of saying if x goes to y, and x prime goes to y prime, then the distance from x to x prime should resemble the distance from y to y prime. I know that sentence is kind of hard to parse. If you translate that to transport language, you now have two manifolds you have to deal with, right? Like the two brains, mine and Mazzy's here. His is much larger, so probably his distance is biased a little bit. But that aside, we have that we want the two distance functions to look the same. And I get that by taking the product of gamma and itself over two different pairs of variables. Aesthetically, this seems very similar. Sadly, while transport is polynomial time solvable, this is NP hard. And so to make a long story short, essentially, one thing we can prove is we can get a local optimum to this problem extremely easily by kind of ignoring one of those two quadratic variables and treating it like a linear problem and iterating. And you can show actually unconditional convergence in that case. And what you get is something that qualitatively we couldn't break, which actually I think motivates an interesting math problem that somehow, from a computer science perspective, like computing a smooth map from one domain into another is this well-known, really difficult quadratic problem. And somehow doing the most naive numerical technique possible, I was able to take this 3D scan, map it to another 3D scan, to Bender the robot, to a point cloud, to the toilet sign outside of my office. And in each case, actually, you get a relatively smooth, if somewhat fuzzy mapping, where again, the fuzziness comes from some entropy hiding inside. Okay. And then, of course, as an extension, we said, okay, well, now that we solved mapping, let's solve something even harder and find Barycenter of a collection of metric spaces. This is a non-convex problem wrapped around another non-convex problem. And purely empirically, it seems to do a reasonable job. So we have these point clouds that are digits that are handwritten. These all have different numbers of points and so on. And when you take the Barycenter, just by essentially doing gradient descent on your distance matrix, you actually get kind of the, I don't know what you call it, like the platonic ideal of these different handwritten digits, which is, we have no explanation for it at all. This is purely just for fun. Okay, so I think we have nowhere near enough time to show you some of the other fun things that we're thinking about. But the basic takeaway here is that transport and associated matching tools are extremely nice ways to think about a lot of geometry problems. And now that we know how to compute these things in less than a ridiculous amount of time, we can use them in lots of modeling and application scenarios. And that's really what we're after in our group, right? At the end of the day, we have collaborators in graphics and medical imaging and so on who really could care less about this beautiful theory of transport and are instead excited about these nice images that we're able to show. And that somehow we're able to sort of not give up theory, for practice here. And that's a really exciting part. So with that, if you like this kind of stuff, we have a graphics symposium coming up. I should advertise to all of you guys. And most importantly, of course, we're seeking collaborators for our group in the math department. So if you have cool ideas that are in need of some help with people in our background, do let us know. But with that, I'm happy to take your questions, or my office is around the corner, so happy to chat anytime. So thank you for your time.
In the Wasserstein Barycenter example that you gave, I sort of missed what was the numerical trick here that you were using. I mean, is it really important for you to actually map the points to the continuous rather than the other way around? Right?
Yes. Okay. Yeah. So the basic observation is that if you have a finite collection of points that you map to anything, then you have a finite number of variables, although your objective function might be hard to evaluate, right? And so essentially, the trick here is that by sampling from these distributions, you can get a stochastic estimate of the gradient with respect to that finite set of variables. And that when you kind of assemble that with a clever kind of geometric trick, what you get is a relatively efficient algorithm for computing this stuff. Yeah.
Another question? All right, so thanks.
Yeah, thank you.